Okay, welcome to topic 3, chemical bonding. So we'll begin with the overview. Now, if you're using this at home, okay, and if you have available the PDF file of the lecture notes, each one of these topics, and I'll just move my mouse onto the screen to show you, each one of these is actually clickable, and you can click on that and it will actually take you to the section of the lecture notes, so you can go straight to the topic that you're interested in. Okay, so today we're going to have a look at electronegativity, dipoles and bond polarity, bonding modes for covalent compounds, writing Lewis structures, VSEPR model of chemical bonding, hybridization of atomic orbitals, and geometry and molecular shape. So we'll begin by discussing the periodic table. So in the previous week we introduced the periodic table and explained that the periodic table is arranged in a particular way so that elements that are above or below each other will have similar properties because they're going to have a similar outer shell electronic configuration. So for example, if you were to draw the electronic configuration of fluorine, it's going to have a similar outer shell electron configuration to chlorine. So fluorine will finish on 2p5, whereas chlorine will have 3p5, bromine will have 4p5, and so on. So they're going to have similar reactivities, okay? And there are other trends on the periodic table as well. So there's a few little, we call them periodic trends, where we can make generalizations about the properties of different atoms depending on where they're positioned in the periodic table. All right. So let's take a look at this concept. You can see here, now this is a scan of a textbook page from the textbook. We've got here some lithium on the left here. What would happen if we were to add some water to some lithium? It would get very fizzy. It would make some lithium hydroxide and some hydrogen gas. It would also produce some heat. You can see a bit of steam coming off there as well. If we were to do the same with some sodium, you'd find that the reaction's a lot more energetic, and potassium even more energetic. In fact, as we go further down, that column, or group as it's known, they become more and more reactive. And there's a YouTube clip you can have a look at as well, just to show that they do become more and more reactive, and eventually they become explosive. Okay, and chlorine and bromine and iodine also have similar properties as well. Okay, we can discuss why this is later on, but for the moment the important part is that elements that are above or below each other on the periodic table, so if they're in the same group, in other words, or the same column, are going to have similar reactivity. So you can see here the periodic table is categorized. It has some groups and they're labeled, so group 1A, group 2A, for example, and so on. And they've got some rows or periods. Okay, so the groups are the columns and the rows are called the periods. Now let's have a look at a periodic trend. So on this slide as well, we're actually indicating our first periodic trend that we're going to learn about, and that's that the elements will increase in atomic radius as you move from the right to the left. Okay, as you move from top to bottom, they're also going to increase as well. So the largest is going to be francium down there in the bottom left. It's got an atomic number of 87. Okay, and one of the smallest is going to be fluorine. So as we move diagonally down into the left, our elements increase in atomic radius. Okay, you might ask yourself, well, why is this? Because as we're moving from left to right across a row or a period, we're actually accumulating more electrons, aren't we? But you need to consider as well, those electrons are being filled into a degenerate orbital. So they're going to be in an orbital of the same energy level, the same distance from the nucleus. But the nucleus is accumulating more protons, and those protons are going to pull those electrons in. So in this way, fluorine is going to be smaller than oxygen, oxygen is going to be smaller than nitrogen, nitrogen is going to be smaller than carbon, and so on. And as we move down, obviously they become larger because we're moving up to higher energy level orbitals, which are going to be further away from the nucleus. Okay, but the important thing is the trend is down and to the left, increase in atomic radius. All right, and here's a diagram illustrating that. Okay, so fluorine's quite small, helium and neon quite small, cesium quite large, and we don't go all the way down to francium in this example. Let's have a look at another periodic trend. So this next trend is the increase in ionization energy or electronegativity. Okay, so it's going to be the increase in the first ionization energy. So as we move up and to the right, we're increasing the ionization energy. So what is ionization energy? Well, ionization energy is the energy that it would take to remove the first electron from that atom. Okay, so lithium, for example, if we're going to compare lithium to fluorine, lithium is going to happily lose an electron. And when it loses an electron, it will gain a positive charge. So we'll have a lithium cation, so we'll have a Li+, in other words. Fluorine, it doesn't want to lose any electrons. Okay, simply put, remember that the elements, they kind of want to be like the noble gases. So for example, fluorine or chlorine or bromine were to gain another electron, then they would be a bit more like the corresponding noble gas. So fluorine doesn't want to lose an electron, it wants to gain an electron. Okay, so it's going to have an increased ionization energy. It's going to take more energy to remove an electron from fluorine. And lithium, on the other hand, it's happy to let go of its electron, has quite a low ionization energy. Okay, francium's got a very low ionization energy. So remember that video that we were just taking a look at where our alkali metals were very reactive. That's if you had a look at the YouTube video, or the diagrams where we had sort of sodium catching fire, where we've added some water, whereas potassium is more explosive. Okay, that's because it's got a lower ionization energy. It's going to lose that electron more readily. It's going to be more reactive. All right, let's have a look at another periodic trend, the increase in electron affinity. So as we move up and to the right, again, we've got a greater electron affinity, and it's not surprising that say fluorine or chlorine or bromine would want to gain another electron. Okay, whereas lithium, sodium, potassium, rubidium, they're on the left hand side, they don't want to gain another electron, so they've got a low electron affinity. Alright, so up and to the right, electron affinity. So let's have a look at the foundation of a chemical bond. So we haven't really discussed chemical bonding yet in this course. We've just had a look at periodic trends. So these are something, okay, there's not very many things in chemistry that you need to memorize. Periodic trends are something that you might want to commit to memory, but if you understand, or if you think about why the trends are occurring the way they are, you might find that it's fairly obvious. Okay, let's have a look at some chemical bonding now. So when we're forming a chemical bond, now let's not worry too much about what kind of bond it is just yet, whether it's covalent or ionic. We'll learn about that soon. In fact, this is going to be a covalent bond if you're curious. So we're forming a chemical bond, is the important part, between two hydrogen atoms. Okay, so if these two hydrogen atoms are too far apart, they're not going to be able to have a bond with each other. Okay, they begin to interact as they move closer together, and there'll be an optimal distance that they like to sit where they're bonded to each other. Okay, if they're too close, they won't like that, because remember their nuclei, which is the plural of nucleus. Okay, nuclei is the plural of nucleus. We don't say nucleuses. So the nuclei are too close together, so they're going to repel each other, because the nuclei are both positive, there'll be an optimal distance that they like to sit from each other where they don't have that repulsion from the positively charged nuclei, but they're able to comfortably share electrons. And this is what chemical bonds are. It's the sharing of electrons in the terms, well, when we're talking about a covalent bond, okay? Ionic bonds are a little bit different, but this type of chemical bond, this covalent bond, it's the sharing of electrons. And there's going to be an optimal distance between the two hydrogen nuclei where this is occurring. Not too close, not too far. It's like the Goldilocks distance. And we find at this point we get some stabilization, and this is called stabilization. Okay, so there's two main types of chemical bonds that we're going to learn about. There's covalent and non-covalent. Okay, so the covalent interaction involves the sharing of an electron pair. So two electrons being shared between two atoms, and they're relatively strong. They're the strongest kind of chemical bonds. These are the chemical bonds that are present in diamond, for example. Okay, they're also the chemical bonds that hold together a lot of your DNA and these types of things. They're quite strong. So the two nuclei are held together by their simultaneous mutual attraction to the electrons of the bond. Okay, so now let's discuss non-covalent interactions. So non-covalent interactions can include electrostatic interactions or ionic interactions. They occur between cations and anions. So an ionic lattice is a 3D structure made by positioning of ions of an ionic compound in the solid state. So we'll have a look at a diagram of what this actually looks like soon, okay? If that doesn't make much sense, don't worry too much about that. The important part is that it's an electrostatic interaction, okay? There's actually a complete transfer of electrons in an ionic interaction, and then there's an electrostatic interaction. So these are the kind of interactions that exist in something like table salt, sodium chloride, okay? Also, as well as ionic, that's the main one, ionic, we've also got some lesser interactions that are also important to learn about. These include hydrogen bonds, van der Waals forces, hydrophobic interactions, and dipole ion interactions. Okay, also dipole-dipole interactions as well. We'll have a discussion about these. These are relatively weaker, okay, forces than covalent forces. So let's have a look at ionic compounds. This is going to be a fairly large part of the course. We're going to be having a look at ionic compounds and also naming them. Okay, so you're going to need to know how ionic compounds are held together and how they work, as well as being able to name them and work with them. But we'll get into this later on. For now, let's just learn what they are. So ions are held together by strong forces between the ions called ionic bonds. They're not as strong as a covalent bond, but they're considered to be a fairly strong force. This is a diagram of a crystal lattice. Okay, so you can imagine the green circles are our chloride ions, and the small white circles are sodium ions. Okay, so you can see in the case of sodium chloride, you can't really draw a single molecule of sodium chloride. It doesn't really make sense. If someone says, draw a molecule of sodium chloride, it's maybe not a very sensible question to ask someone to do, because sodium chloride actually exists as a crystal in a crystal lattice. So think about your table salt. They're actually little square-shaped crystals, aren't they? And that's exactly what's happening in these ionic compounds, is that you've got an alternation of sodium ions and chloride ions, and they're bound together in this alternating lattice, okay? And this is how they form a crystal. If you were then to dissolve it in water, they would break apart into their separate ions. Okay, there's our little diagram there. So there's ionic bond, taken, not shared. So the electrons are not shared in an ionic bond. An electron is actually transferred, in this case, from the sodium to the chlorine, causing the sodium to lose an electron. It gets a positive charge. The chlorine gains an electron. It's got a negative charge. And then because one's got a positive charge and the other one's got a negative charge, they're attracted to each other. So they form this lattice, and that's all there is to it. Now let's see how this applies to the octet and the duet rule. So atoms will tend to give up or take on electrons from or into their outer energy level in order to achieve a stable noble gas electron configuration. Alright, so we would expect our chlorine in sodium chloride to gain only one electron, not two. If you have a look at chlorine on the periodic table, if you've got a periodic table handy, have a look at where chlorine is. Right next to chlorine is argon, Ar, right there to the right hand side. Chlorine just needs to gain one electron to be like argon. Okay? It's not going to gain two, it's just going to gain one. And sodium's just going to lose one, because sodium, if it loses one electron, it's like neon. Okay, so sodium loses an electron, our chlorine gains an electron, and now we've got two charged ions, sodium ion and chloride ion, and they're going to be attracted to each other and form the ionic compound sodium chloride. Now, we're not going to cover metallic compounds in any great detail in this course. In fact, this is the only slide that there is on metallic compounds and metallic bonds. Now, they're a special type of bond. They're different from a covalent or an ionic bond, and the electrons can move freely between the different atoms, and this is how we can use metals to conduct electricity. Let's have a look at covalent compounds. Now, covalent compounds are a type of compound where the lattice sites are occupied by atoms which are held together by covalent bonds. Okay, they don't necessarily have to form a lattice. So in the case of water, you can see here we've got an example on the bottom right hand side. The water has formed a lattice when it's frozen, okay? But when it's liquid water, it won't actually form this lattice. So you see those circular dotted blue bonds, okay? Those dots, those blue dots, dotted interactions, they're called hydrogen bonds. We're going to learn a little bit about them later on. They're not as strong as a covalent bond, and they'll occur primarily in water when it's cooled down to its freezing point, and it will form a solid in this lattice. Okay, liquid water doesn't have this structure. It does have hydrogen bonds, but they're able to freely move past each other, and this is the reason why water actually expands when it's frozen, because it forms this lattice, and this lattice is actually larger than it could be. Okay, so their packing is less dense. But the other type of bond, the covalent bond, that's the bond between the oxygen, which is the red one, the large red one, and the hydrogen atoms. Remember, water is H2O, so those hydrogens are the two, well, they're like a light blue colour, or they might be like a white colour, and you can see those stick bonds are the covalent bonds, where we're actually sharing two electrons. And the covalent compounds also follow the octet and the duet rule. So, reacting atoms of nonmetals share electrons in order to achieve an outer arrangement of electrons identical to that of a noble gas. So what that statement means is that, okay, these atoms also want to be like a noble gas, but they're not going to give and take electrons like the ionic compounds do. They're just going to share them. So in the case of HF, or hydrogen fluoride, our hydrogen wants to gain an electron to be like helium, and our fluorine also wants to gain an electron to be like neon. They can both do this by sharing two of their electrons. So now the fluorine effectively thinks that it has the electron arrangement of neon, and the hydrogen thinks that it has the electron arrangement of helium, if you like to think of it that way. Okay, so the hydrogen is now surrounded by two electrons, and the fluorine is now surrounded by its 8 electrons that it wants. So in this way, it can be said to be forming an octet. So in its outer shell, so in its 2p shell, it's got 8 electrons, okay? Something like chlorine might want 8 electrons in its 3p shell. This is why we call it the octet rule, because it's 8s, groups of 8. The duet rule really only applies to hydrogen and helium, I suppose, but hydrogen's the important one because helium really isn't very reactive. And you can have double bonds, okay, where you're sharing 4 electrons, and triple bonds, where 6 electrons are shared in between 2 atoms as well. We refer to them as double bonds and triple bonds. Now let's discuss some intermolecular forces that we might encounter as well. So, Our intermolecular forces are important as well. These are a little bit like the hydrogen bonds, okay, that we saw occurring in water when it was frozen. There's also London dispersion forces, dipole forces as well, and all of the above can be present in solids. Now here's an example of hydrogen bonding occurring between two water molecules. Okay, these are intermolecular forces because they occur between different molecules. They're a weak force. These are the forces that stop water from evaporating. Okay, when we heat water up, it's able to then overcome this hydrogen bonding and thus evaporate. Okay. Now, let's have a look at dipole-dipole forces. So, when you've got one atom that's got a little bit more of a negative charge than another atom, so for example, in this case, oxygen's got a little bit more of a negative charge than the carbon does, when we've got a chemical bond between carbon and oxygen, you're going to have a partial negative charge on one side and a partial positive charge on the other side. If it helps you, you might think about this as being a little bit like a magnet. I don't like to use that analogy though, because magnetism and electrostatic attraction are two different things. But the positive end of the molecule is going to be attracted to the negative end of the molecule and vice versa. So you're going to have what's known as dipole forces. Okay? And this is going to operate in what's known as a polar molecule. Now, London dispersion forces can occur in any kind of a molecule. So even if a molecule isn't considered to be polar, okay, you can also have London dispersion forces. Now, this is the weakest kind of intermolecular forces. So this is the kind of intermolecular force that exists in something like, say, petrol. So think about petrol. It's a liquid, but it's kind of doesn't really enjoy being a liquid. So it's not very strongly attracted to itself. It wants to evaporate very quickly. It's got some strange properties, okay? And this is because it doesn't have any strong forces holding the molecules together. It's just got these dispersion forces. Now these occur due to a random arrangement occasionally of electrons, and this is probability is unlikely that this asymmetrical distribution is going to occur. That's why they're weak forces. It does happen though, and that's why we've got these weak forces. Hydrogen bonds are quite strong. They're not as strong as a covalent bond or an ionic bond, but they're a rather strong bond. Okay, they're stronger compared to, say, dispersion forces, and they occur between highly electronegative atoms such as oxygen, nitrogen, and to a lesser extent fluorine. You probably won't see that one very often. Okay, but when we've got an oxygen-hydrogen bond, it's a covalent bond, but it's very polarized. So that the oxygen's actually quite negative compared to the positively charged hydrogen, so it can then undergo hydrogen bonding, the kind that we see in water. So here's the relative strengths of the different kinds of forces that we've covered. So London dispersion forces are the weakest, then dipole forces, hydrogen bonding, okay, and our ionic bonds are a bit weaker than our covalent bonds. And there's also metallic bonds in there as well, which we won't cover too much in this course. Now I've mentioned electronegativity. Okay, just prior then I actually did mention the term electronegativity, but we haven't really covered what it is just yet. So what you'll find is that as you move up and to the right on the periodic table, we actually increase in electronegativity, so our fluorine has the highest electronegativity and our francium has the least. Okay, and this is, you can think of this as how relatively negatively charged an atom is. And this is important in determining whether a bond is going to be, say, ionic or covalent. There's our trend. So how do we tell if a bond is ionic or covalent? So the greater the electronegativity difference between the two atoms, the more ionic or polar the bond. Okay, so chlorine bonded to chlorine is going to have no difference in electronegativity because chlorine and chlorine both have the same electronegativity value. Let's go back a slide. You can see Chlorine has electronegativity of 3.2. So 3.2 minus 3.2, we get 0. So there's no electronegativity difference between the two. It's going to be, down here, non-polar covalent. Okay, so oxygen-hydrogen bond has an electronegativity difference of 1.2. It's going to be polar, but still covalent. Sodium and chlorine, 2.3. So now we know that sodium chloride is going to be an ionic bond. It's as simple as that. So there's a little bit more to polarity than meets the eye. Yes, it's to do with having compounds of different electronegativity, but what about this example where we've got carbon dioxide? So carbon dioxide is linear, which means the molecule is all in a straight line. So we've got carbon in the middle, we've got oxygen either side. Okay, so in our carbon dioxide, what's going to happen is that although there is a dipole, okay, although the oxygen is more negative than the carbon, it's actually going to have an equal pull. It's like a tug of war, really. It's pulling equally on this carbon atom in the center. So we're going to add the dipoles as vectors, and there's going to be no net dipole moment, meaning that carbon dioxide is non-polar. So at first glance you might think, oh yes, that's going to be a polar molecule because we've got carbon and oxygen, but it's actually evening itself out. Water doesn't do this. We can see water down the bottom there where we've got H2O. It's actually got this bent configuration. So because it's bent, if you imagine that it's a tug of war, those two hydrogen atoms are pulling unevenly on the oxygen. It would move in a tug of war. It has a dipole moment. Water is polar. And the same with ammonia above it. So NH3 ammonia, it has a dipole moment. Okay. It's polar. All of these are polar. So general rule is if polarized bonds are arranged symmetrically in a molecule, their dipoles will cancel and the molecule will not possess a dipole moment. So i.e., the molecule will not be polar. And here's an example of some amino acids, and you can see that larger molecules have regions that are polar and regions that are non-polar. Okay? So you actually get a mixture of polarity within the same molecule. And this will be important later on as you start learning about amino acids in biology and later on in biochemistry as well. There's tyrosine, proline, serine, glycine, aspartic acid, and arginine. In the diagram below, which lines represent the hydrogen bonds? It is going to be the dotted blue lines. Question, how would the intermolecular forces influence the boiling point? Okay, think about this one. Intermolecular forces. So remember, our hydrogen bonds are the strongest intermolecular forces, so they're going to cause the boiling point to be higher, such as in water. Whereas London dispersion forces have the least amount of attraction between the molecules, so they're going to result in lower boiling points. So which of the following two compounds would have the higher boiling point, ethane or hexane? Now, they're very much the same in the sense that it's just carbon and hydrogen. Okay, so how do we compare the two? Well, in the case when you've got the same types of bonds, then you have to have a look at the size of the molecule. And the larger molecule, hexane, is going to have a higher boiling point because it's got more surface area to have intermolecular forces such as London dispersion forces. Okay, let's have a look at the bonding model for covalent compounds. So we use the localized electron model. It's based on atoms in a molecule sharing pairs of electrons using their atomic orbitals. So bonding pairs of electrons and non-bonding pairs of electrons exist, and we'll discuss these later on. So the model has three parts: the Lewis structure of molecules, the valence shell electron pair repulsion model of molecular shape, determining orbitals which hold the bonding and lone pairs of electrons involves hybridization of orbitals. So we're going to have a look at Lewis structures via CPR, theory, and hybridization. Let's begin by looking at how we write our Lewis dot structures. First, we sum the valence electrons, then we use a pair of electrons to form a bond between each pair of bound atoms. We'll arrange the remaining electrons to satisfy the octet rule or the duet rule. If you have too few electrons, then you can use double or triple bonds. If you have too many electrons, okay, sometimes our central atom can actually accommodate extra electrons in its empty d orbitals if it's in row 3 or greater. The best way to learn these is to practice them. So practice your tutorial questions, go to the tutorials, go to group learning if you're having some trouble with these. Once you understand how to do them, it's actually quite easy. Okay. Second row elements, carbon, nitrogen, oxygen, and fluorine, always obey the octet rule. Okay. Beryllium and boron can have fewer than 8 electrons, and they're termed the electron deficient compounds. And your third row and heavier elements often do satisfy the octet rule. However, they are able to accommodate more than 8 electrons using unoccupied d orbitals. That's if it's the central atom and if it needs to. You'll understand what this means as you practice some more. So here's some practice questions that you might like to try. Okay, so these practice questions, you can do those in your own time. I won't go through the answer to these right now. Okay, we'll leave that for later on. You'll go through a lot of these in the tutorial as well. So take your time, you can practice these. Let's have a look at resonance now. So resonance is a bit of a unique concept in chemistry. Okay, so let's have a look at the resonance of NO3-, the nitrate ion. So in nitrate,